All right, so let's talk about some trends in entropy, which things have more entropy, which things have less entropy, why, that kind of thing. So let's think back to, again, delta S entropy. You can kind of think about it as disorder, but I like to think about it more like kind of dispersion. How dispersed is the energy? How dispersed are the molecules? Another good way to think about it is from the original definition of this K, L, and W, where this W is the number of microstates. So ways you can arrange something. Right, so the more ways you can arrange something, the more entropy your system is going to have. Volume. All right. So let's first talk about, solid, liquid, gas. We already talked about this. As you go from left to right, you increase entropy, right? And that's because your molecules become more dispersed, your energy becomes more dispersed, you have a greater number of ways to organize things. For example, if you think of a solid, if you have, kind of A, B, these things can't switch together. So you can only really have kind of one microstate. Of course, there's vibration there, so you can actually have multiple microstates. But if you think about a liquid, you could swap these out. They could roll over one another, so you can see how that has more microstates. And then about a gas, you're talking about things being over here, being close together, being far apart, all kinds of different things. So when you get to from solid, liquid, gas, you increase the amount of entropy. Oops, it should be energy. Entropy increases. All right, next up, we have these kind of list of noble gases that you can see from this table. So generally, as you go down the periodic table within a column, the entropy increases. So we'll go with bigger noble gas. Causes an increase in entropy, right? So this is actually kind of a bit more of a complex topic, but basically has to do with the kind of energy levels getting close together so you can disperse the energy some more. I just thought I'd throw it in there because I see it often in kind of standardized exams. So just be for a lookout if they ask, which noble gas has more entropy, it's going to be the bigger one. Next up are different types of allotropes. Allotropes. So what is an allotrope? It's a different form of an element in the same phase. So different form of element in the same phase, right? And the general thing you kind of want to think about here is more freedom to move, more ways you can organize that system, more entropy. Increase, we'll go with microstates, and there, thus more entropy. So the most common example of this is diamond and graphite. Right, the most common example is diamond and graphite. So up here up top, we've got diamond, and you can see these are sp3 hybridized carbons. And so they're actually locked in. They've got bonds coming kind of from all four sides, if you think about it. And so they're actually, this carbon right here is actually locked in. It can't move very much at all. And so its entropy is going to be very small. It's not going to be able to organize itself in different ways. You're not going to have a lot of micro states. Down here, though, these carbons over here, if you think about this carbon, it's an sp2 hybridized carbon. And so again, this carbon won't be able to move left or right, but it can actually move up and down. Or no, not up and down, my bad. This whole sheet can rub against each other, right? These planes can move from one side to the other, while the other carbon cannot. And so this increased range of motion has an increased amount of entropy. So generally, look for ability to move. That'll tell you that you have a higher entropy. The next trend is that generally the more complex the molecule, the more entropy you have. So this is kind of the same thing with the allotropes. It's all about kind of degrees of movement, ways you can organize things. So here's carbon monoxide, right? And so you can think about what movement this molecule can do. Well, it can float around like a gas, but it can also kind of stretch this bond or shrink the bond, right? This bond can vibrate, so that's what it can do. Well, if we take a look at a more complex molecule, something like this guy can do this shrinkage and this stretchage on all of these bonds. But then you can also think about these angles right here. These angles can wiggle around and they can move as well, right? So they're both gases, so they can move around, right? They can fly through the air, but this one has more ways to wiggle around, to switch around, to make more microstates, and so this side right here has increased entropy. And if you look at it, here's carbon monoxide, here's the C2H4. If you look at the molar mass, they're about the same, so the difference isn't in terms of molar mass, right? They're about the same in terms of molar mass, but if you look at their entropy, this one is 197.7 joules per mole Kelvin. This one is 219.3 joules per mole Kelvin. And again, that's just a general trend. The more complex the molecule is, the more ways it can reorganize itself, the more microstates you can have, the more entropy you can have. In this picture right here, this picture right here just shows you different types of motions these molecules can have. So again, more types of motions you have, more ways you can organize yourself, more entropy. All right, so we'll just say more freedom of movement, more microstates, more entropy. Another thing, dissolving things, right? We kind of already went over this. If you have some solid and you want to dissolve it into a liquid, which side is going to have more entropy? Well, dissolving things increases the entropy, because you can think about these molecules right here are trapped, they can't move. And then once you dissolve them, these guys are free to move around, and so you can organize them in more ways and increase the entropy. So again, dissolving things, generally an increase in entropy, which we can see is a major driving force of spontaneity. Next, we'll go over kind of another type of measurement that gives you spontaneity.